organic chemistry based on the first unit, structure and bonding. This unit is very important and very helpful to understand whole chemistry. In the previous episode, we learnt about bond energy. Bond energy means we can predict which bond will be stronger and which bond will be weaker, and how much energy will be required to break that bond. Concepts of the bond length like carbon-carbon single bond, carbon-carbon double bond, which bond will be shorter and longer, and what are the factors which are affecting the bond length, and concepts of the bond angle also, which can be derived with the help of hybridization. In the hybridization, we learnt about sp3 hybridization, sp2 and sp hybridization. These hybridization concepts are very important, as with the help of those concepts only we can predict the geometry of the molecules like water, ammonia, methane, ethylene, etc. Now in this episode, we will concentrate on basic concepts of delocalized chemical bonding and resonance. These concepts are very important as far as understanding of the concepts of conjugated system is concerned. As we know, aromatic compounds are very important for the industries also. So, these concepts help us to understand which product will be formed, in what amount it will be formed, and what will be the rate of the reaction, and various isomers. To understand delocalized chemical bonding, first of all, we will have to revise what is covalent bond. As we know, covalent bond is formed by overlap of pure or hybrid atomic orbitals. This overlap may be between 1s and 1s orbital, as happens in case of hydrogen molecule, resulting in the formation of sigma bond, or this overlap may be the sidewise overlapping of the p orbital and another p orbital, which results in the formation of pi bonding. To understand overlapping of the hybrid atomic orbital, we can discuss the case of benzene. As we can see, in benzene, each carbon atom is sp2 hybridized. Each carbon atom which is having sp2 hybrid atomic orbital will overlap with its neighboring carbon atom, and in this way a sigma bond is being formed. Now there are two possibilities when covalent bond is being formed. Electrons participating in the bond formation may remain in between the participating atom, resulting in the formation of localized bond, or these electrons may be delocalized between 3 or more atoms. In this way, it may give the delocalized bond formation. We know that all type of sigma bond falls under the category of localized bond. Why? Because in case of sigma bond, direct axial overlapping takes place. So, electrons remain between participating atoms only. As we can see here, in beryllium hydride molecule, how 1s orbital of the hydrogen atom is overlapping with the sp hybrid atomic orbital of the beryllium, and in this way a sigma bond is being formed, and these electrons present in this orbital remain localized here only. So, it is the case of localized bonding. Now, all type of pi bonds can be divided in two categories. They may be localized or they may be delocalized. To understand the case of localized bonding, ethylene is the simplest example. We can see in ethylene, first of all, a sigma bond is being formed by the overlapping between sp2 hybrid atomic orbital present on one carbon atom and sp2 hybrid atomic orbital present on another carbon atom. Then next, a pi bond is being formed. Pi bond is formed by the sidewise overlapping which is taking place between unhybridized p orbital present on one carbon atom and unhybridized p orbital present on second carbon atom, and they are overlapping here. Electron present in the pi bond, that is 2 electrons, will remain localized here only. So, it is called the localized pi bonding. To understand case of delocalized pi bonding, benzene is the simplest and best example. Here we can see how 6 carbon atoms are being joined together through the sigma framework. Now, since each carbon atom is sp2 hybridized, it possesses a remaining unhybridized p orbital. So, unhybridized p orbital here, then here, then here. So, total there are 6 unhybridized p orbitals. So, these orbitals, electrons present in these orbitals will be delocalized over whole of the ring, and a resulting delocalized pi MO is being formed. So, in this fashion we can see electrons present here and here will not form a simple pi bond between two atoms only, but they will be delocalized over whole hexagon of the carbon ring. To understand that what are the characteristics of the delocalized chemical bonding compounds, we can see here the case of 1,3-butadiene, means it possesses 4 carbon atom and 2 double bond, 1 double bond between first and second carbon atom, and then third and fourth carbon atom. Hence, it is called 1,3-butadiene. It possesses one or more bonding orbitals spread over 3 or more atoms. We can see here that pi bond will not remain localized here and here only, but it will be delocalized over all the 4 carbon atoms. Such compounds cannot be described by single Lewis structure, as happens in case of compounds like ethylene, which does not show delocalized chemical bonding. We can see example of vinyl chloride, where this is one of the Lewis structure and this is the another Lewis structure. This structure is having a plus charge and minus charge. So, overall molecule is same, it is electrically neutral. In the valence bond approach, resulting wave function for the delocalized molecular orbital may be represented by this equation. Psi1, Psi2, these are the wave functions for the various canonical form. Canonical form means various Lewis structures. So, we can see how delocalized MO is linearly related with the wave functions of the canonical form. This delocalized chemical bonding is very important and it helps us to understand change in the bond length, what we will expect from the simple structure and what we are observing actually. This also helps us to understand stability of the molecule. Molecules like 1,3-butadiene and benzene are quite stable. We can take the example of benzene. Here we can see benzene is a resonance hybrid of all those canonical form, also called resonating structures. Here we can see this bond is having double bond, same bond here it is carbon-carbon single bond, here again it is single, here again it is double. So, these are various possible canonical forms for the benzene molecule and it is the overall resonance hybrid. Representation of real structure as weighted average of canonical form or resonance structure is called resonance. We can further understand this concept by taking example of rhinoceros, which is considered to be resembling the characteristics of unicorn a hypothetical animal, and dragon, another hypothetical animal. So, unicorn and dragon can be considered as canonical forms, and overall resonating hybrid is the actual animal, which is rhinoceros. Now, change in bond length, which is observed in case of benzene. On the basis of this Lewis structure, we will expect that this bond length will be equal to the value of carbon-carbon double bond. However, this bond length will be equal to the value of carbon-carbon single bond. In the same way, this will be double, then this will be single. So, expected bond length for the carbon-carbon single bond should be 1.48 angstrom. This is the value for the sp2 hybridized carbon atom overlapping with another sp2 hybridized carbon atom. For the carbon-carbon double bond, expected bond length should be 1.32 angstrom. But actually, in case of benzene, what has been observed that all the carbon-carbon 6 bond lengths are identical and value is 1.40 angstrom. We can see that this value lies in between value of the 1.48 and 1.32 angstrom. So, our bond is not strictly speaking single bond or strictly speaking double bond, but it is somewhere between these two. So, it is called partial double bond character. Now, how we can understand the stability of the benzene with the help of delocalized chemical bonding? As we expect here, if this double bond would have been strictly double bond, then electron density would be quite high. Here again electron density would be quite high, but due to resonance what happens, these 2 electron plus 2 electron here plus 2 electron here, they get delocalized over whole ring. So, overall electron density on any carbon atom is decreased in comparison of the what we expected from this. So, stability is increased. As we know, charged species, more the charge and less will be the stability. So, here since charge on any particular carbon atom is decreasing, means electron density is decreasing, hence stability is increasing. Another important concept is concept of resonance energy. Resonance energy is nothing but difference between energy of resonating hybrid and that of the most stable canonical form. It makes the molecule stable, that is lower heat of combustion and lower heat of hydrogenation. We can further understand this thing by taking this example. Here we can see that cyclohexene, this molecule, if it is adding 1 mole of hydrogen in presence of catalyst and being converted to the cyclohexane, it is showing enthalpy of hydrogenation as 28.6 kilocalorie per mole. Now, on the basis of this value, what we can expect that if 3 moles of hydrogen are being added to 135 cyclohexatriene molecule, which is considered to be a hypothetical molecule, then we will get the enthalpy of hydrogenation as thrice of this value, 85.8 kilocalorie per mole. Now, benzene, if we add 3 moles of hydrogen here and we are converting it to cyclohexane, what heat of hydrogenation we are actually observing is quite low. It is 49.8 kilocalorie per mole. Here we are getting 85.8. This is on the basis of theoretical calculations only, and here we are getting 49.8. This is the actual value. So, difference between these two values is the resonance energy. Here we can see this is the difference between the value of the canonical form and the resonating hybrid. So we can see how this resonance hybrid is much more stable than the hypothetical canonical form, and it makes the molecule stable. There are certain rules of resonance which are helpful to understand which compound will show the resonance mechanism and which compounds will not show the phenomenon. We can see that it involves delocalization of pi or non-bonding electrons. 1,3-butadiene is the case of delocalization of pi electron. Here we can see how this pi bond is moving here, and we are getting a new pi bond formed here, and at the same time this pi bond is moving here and we are getting a negative charge here. In the same way, since this pi bond is moving, this carbon is becoming electron deficient and hence the plus charge. Vinyl chloride is another important example where we can see not only pi but non-bonding electrons are also participating in the resonating phenomenon. Here we can see that non-bonding electrons present on the chlorine atom are being delocalized over the carbon-carbon double bond, and we are getting a new negative charge here and a positive charge here, since non-bonding electrons which were present entirely on the chlorine atom earlier, they have now shifted to the adjacent bond. So, slight deficiency in the electron density will take place and it will get a plus charge. This is very important rule. Greater the number of resonating structures, more would be stabilization. Here we can compare the stability of various ions, like we have tried to compare stability of allyl carbonium ion with the stability of benzyl carbonium ion. We can see this is the structure of allyl carbonium ion. Here a plus charge is present, so this will be attracting this loosely bound pi electrons towards itself, and a new carbon-carbon double bond is being formed. Since electrons are migrating from here, so this carbon will face slightly electron deficiency and a plus charge arises. So, allyl carbonium ion shows two resonating structures. If we compare allyl carbonium ion with benzyl carbonium ion, here we can see CH2 plus is bonded to a conjugated system. So, here because of the presence of this plus charge, pi bond electrons present here will migrate from here to here and a plus charge will arise here. Here you can see, and this bond will become double bond. Since here carbon is having valency 4, which is its normal valency, it will not show any charge. Here, due to the presence of plus charge, again it will be attracting the neighboring loosely bound pi electron. Here it is very important to note, it is the electrons which move, not the positive charge. So, these pi electrons will move from here to here and a new pi bond is being formed. Due to movement of these electrons, this carbon will face electron deficiency and hence a new positive charge is generated. Simultaneously, it will attract pi electrons and a new pi bond will be formed here. So, here we can see that benzyl carbonium ion is showing more number of resonating structures than allyl carbonium ion. Hence, it is much more stable. Another important rule for the resonance is that resonating structures must be planar. This is possible only when each and every atom is sp2 hybridized. Otherwise, this delocalization between the p orbitals which are lying in a parallel fashion will not be possible. Each structure must have same number of unpaired electrons. Here we can see the example of triphenyl methyl free radical. This carbon atom possesses a single electron. This electron will move here and simultaneously this pi bond will break in the homolytic way and one of the electron will move here. So, together they will form a single bond, means second pi bond, and second electron will move here. So, we will get a new free radical. Again we are having same number of unpaired electrons. Again homolytic fission will take place and this electron will move here, and from the neighboring pi bond one of the electron will come here and one of the electron will move here. So, together they will form a new pi bond here and a new radical will be formed here. So, on the basis of all those structure, we can see that each structure is having same number of unpaired electrons. So, it is the only electron which is moving, not the atom, and overall number of unpaired electron remains same. Resonance hybrid is intermediate between various resonance structures and it is not a mixture of them. As we can see here, example of carbonate ion, where we can see these three are the various canonical form and it is the overall resonance hybrid. We can see here carbon oxygen bond is single bond, here it is single bond and here it is double bond. So, out of these three resonating structures, in one structure this carbon oxygen bond is of double bond nature and in two it is of single bond. So, overall in the resonance hybrid, character of this bond is partial double bond character. If we consider the charge also, here we can see this oxygen is having -1 charge, in the second structure also it is having -1, in the third structure it is having no charge. So, basically -2 charge spread over 3 structures. So, overall in the resonating hybrid, what will be the situation? It will be overall -2 divided by 3. So, -2 by 3 negative charge. So, we can see resonance hybrid is intermediate of all these three, it is not a mixture of them. Another important rule is that resonance hybrid is more stable than resonating structures. This we have learnt when we were understanding the concept of resonance energy, where benzene is the much more stable than its hypothetical structures of 1,3,5 cyclohexatriene. Here we can see once again the same diagram, that benzene is having lower heat of hydrogenation than heat of hydrogenation predicted for the 1,3,5 cyclohexatriene molecule. Resonance always increases stability of the molecule, and if a molecule is being stable, it will be less reactive. As we can understand, for the benzene and its homologues, they are quite stable in comparison of alkene, which is not showing any delocalized chemical bonding, as we see in case of ethylene molecule. They are quite reactive. Energies of various canonical structures must be nearly same. This is very important. If energy of various canonical structure are not of nearly same value, then this delocalization will not be possible. At the end, we will revise all the concepts of delocalized chemical bonding and resonance which we have learnt in this episode. Resonance is the process where generally p electrons or sometimes non-bonding electrons also, as we learnt in the case of vinyl chloride, they can be delocalized by exchanging with double bond and single bond. So we can see how electrons are moving over entire system, and it is very important that entire system should be planar, otherwise this delocalization will not be possible. Resonance can be used to delocalize both lone pair of electrons, as we observed in case of vinyl chloride and many other molecules, and this can be helpful to understand the delocalization of cationic charge also, as happens in case of allyl carbonium ion and benzyl carbonium ion, if these cationic charges are adjacent to the double bond. Delocalization of positive charge leads to relatively stable cation, as we have learnt in case of benzyl carbonium ion. Benzyl carbonium ion, since it shows more number of resonating structure, it is quite stable, and in the same way delocalization of negative charge also, it leads to stabilized anion. In this episode, we learnt about various concepts of delocalized chemical bonding, how it is different from the localized chemical bonding, various concepts of resonance, resonance energy and their role in conjugated systems. In the conjugated systems, we studied their application in 1,3-butadiene and benzene. These concepts are very helpful in understanding reactivity of these compounds. In the next episode, we will understand and discuss the application of delocalized chemical bonding in the name of mesomeric effect.